This is mathheals.com, where you can find more links to YouTube math videos and computer science. And let's take a look at infinite limits. Now, infinite limits is where you have a graph that's going to infinity, positive infinity, or it could be. I don't think there's any in this particular section where you're studying x as it goes to infinity, but you got infinity in there somehow. Well, let's look at our first example here. Got f of x is equal to 1 over x minus 2. And it's asking, determine whether f of x approaches infinity or negative infinity as x approaches 2 from the left and from the right. Well, let's just look at the graph of this and then see what's going on. So I'm going to press my y equals, press clear. I'll do 1 divided by, and since we have more than a single x or single number down in the denominator, we have to put parentheses around it. So we'll do a beginning parentheses, x minus 2, closing parentheses, and then graph. And it says determine whether f of x approaches infinity or negative infinity as x approaches 2 from the left and from the right. So what they're really asking, as x approaches 2, this is from the left, that what looks like the negative power. That's how you write from the left side. And they're also asking, what is the limit as x approaches 2 from the right-hand side? That's what the plus means of f of x. Okay, well, from the left-hand side, so I'm coming from the left-hand side, getting closer and closer to x equals 2, you see it's going down forever. So my y value is going to negative infinity. Now I come from the right-hand side. I come from the right-hand side, getting closer and closer to x equals 2, you see the y values go up forever. So it's going to positive infinity. And those will be your answers. Now our second one here actually gives us a graph. We've got f of x is equal to cosecant pi x over 4. Now that blue line there, and we have many of them, actually an infinite number, that represents the vertical asymptote. You don't actually see that. Usually it's written as dotted line, but I was having a little bit of trouble with my my paint package. I couldn't figure out how to make it a dotted line, or a dashed even. So we're studying it as it approaches 4. Well, that's where this blue line is a 4. So let me write this down. So we're looking at the limit as x approaches 4 from the left-hand side of f of x. And we're looking at the limit as x approaches 4 from the right-hand side of f of x. Well, from the left-hand side, getting closer and closer to that blue line. So as x approaches 4, you see my y values are going up forever. So from the left-hand side, it goes to positive infinity. Now from the right-hand side, as it gets closer and closer to x equals 4, I see my y values are going down forever. So that's going to negative infinity. And those would be your answers. Now, this concept here, where you got an invisible line, this is a line you can't see. Where you got an invisible line, the graph skims, gets real close to, but never touches, never crosses, just keeps getting closer and closer to it. That's a vertical asymptote. Now let's talk more about vertical asymptotes. Okay, so we got f of x equals 2x minus 1 over x squared minus 4. And the instructions here are saying find the vertical asymptotes, if any, of the graph of the function. So vertical asymptotes for rational functions. Now rational means you got a single fraction, and specifically we have x's on top and bottom. what we're going to do is we're going to factor the top and factor the bottom. Okay, so for this problem here, the 2x minus 1, can't factor that. But the x squared minus 4, that's a difference of two squares. That factors as x plus 2, x minus 2. Now step 2 is cancel if possible. Well, to be able to cancel these, this would have to be like an x plus 2 or x minus 2. But since this is different than each one of these factors, we can't cancel. And then step 3, set the denominator equal to 0 and solve. And these will give us our vertical asymptotes. So set my denominator equal to 0. So x plus 2 times x minus 2 equal to 0. Zero factor property from college algebra. You get 0 on one side, you factor the other side, you set each factor equal to 0. So I'll set x plus 2 equal to 0 and x minus 2 equal to 0. And that gives us negative 2, and that gives us positive 2. And those will be our vertical asymptotes. Now if I were to graph this, I would see that my graph skims these. Gets real close to it, but never touches, never crosses it. Let's take a look at our next one. Get f of x is equal to x squared minus 9 over x to the third minus 3x squared plus 3x minus 9. Now remember our steps from up above. When you got a rational function, you're going to factor the top, factor the bottom. Well, the top part is the difference of two squares. Bottom part is groupings, 4 or more terms. Top part factors as x plus 3, x minus 3. And the bottom part factors as x squared plus 3 times x minus 3. Okay, so after I've factored top, factored the bottom, then I want to cancel. So that's our first step there. So our second step. I see I have an x minus 3 here and x minus 3 here. So those x minus 3 is going to cancel. And we got x plus 3 over x squared plus 3. Okay, now I've canceled. Now this third step is I want to set the bottom part equal to 0. So I'll set x squared plus 3 equal to 0 and solve it. This is a square root property. I'll take 3 over, becomes a negative 3. Square root property says if you got something squared equal to the other side, you drop your squared, and you put a plus minus square root around that side. Now we have a negative inside of a square root, and that's going to give us an I with some other stuff. But the fact that we get an I means there is no vertical asymptotes. So if you don't actually get a number here, then there is none. Now if I were to look at the graph of this, again, to plug this in, I'll put parentheses around top, parentheses around the bottom. Anytime you have more than a single variable or single number in top and bottom, you have to put parentheses around it. So I'm going to press my y equals, press clear, at beginning parentheses, x squared minus 9, closing parentheses, divided by, beginning parentheses, x to the third, minus 3x squared, plus 3x minus 9. And closing parentheses, and then graph. Now as I look at this, You notice how if I didn't factor and cancel first, this x minus 3 would have gave us a vertical asymptote of 3. But the fact that it cancels away is what causes it not to be a vertical asymptote. And obviously, if I set the x minus 3 equal to 0, I'd get x equals 3. Here at 3, there is no issue, is there? It doesn't skim it, go up forever. Vertical asymptotes, oftentimes you have a gap in there with rationals. And we obviously don't have that. What we're going to find is what we do have at 3 is we have a hole. So if I were to graph this, the graph doesn't exist at 3. So there'd just be an open dot there. They're not asking you for that, but extra information. And let me save this page, and then we'll do the next problem. Infinite limits page 01.pdf. And save. Okay, so we got f of x is equal to natural log of x minus 5. And this is finding the vertical asymptotes. We have logs. Well, we set what follows our log equal to 0. And solve. So set what follows our log equal to 0 and solve. So like in this problem, we'll take the x minus 5, set equal to 0, and we get x is equal to a positive 5. And that's our vertical asymptote. Now if I were to graph this and take a look at it, press my y equals clear, natural log of x minus 5. You don't have to have closing parentheses at the very end, and then graph. Grab a drink here. Notice how it looks like my graph just stops. Well, the graph never just stops. It actually keeps going down forever. It just keeps getting closer and closer to this line, but never touches it, never crosses it. Just skims it. And the TI3, TI4 isn't very good about logs. They'll always show them stopping. They never stop. They keep going down forever, which is what we're looking at for a vertical asymptote. Let's look at this next one. We got cosecant of pi x. And this is vertical asymptotes of cosecant, secant, tangent, and cotangent. And our first step is to rewrite as a fraction in terms of sine and or cosine. So for this problem here, we got cosecant. We can rewrite that as 1 over sine. So this becomes 1 over sine pi x. Now to find our vertical asymptotes, we'll now, second step, set the denominator equal to 0. and solve. And these will actually give us our vertical asymptotes. Okay, so if I set the sine pi x equal to 0 and solve this. Well, first off, I need to go around and look where sine is equal to 0. Well, got a line here. We're wondering when sine is equal to 0. And I don't know how many of these I need. We'll start there. Well, sine of 0 is equal to 0. Now I go over to pi, and sine of pi is equal to 0. Now what I'm doing, in case you're wondering, is I'm just let's see. Go into the unit circle here. Okay. Sine is our y part on our unit circle. Well, here's y is equal to 0, so 0. And over here, our y part is equal to 0, which is pi. So I'm just using that. Now, if I kept on going around my unit circle, you know, if it occurs here at 0, occurs here at pi, if I go around back to here, this will be 2 pi. So it occurs at 2 pi. And then next one will be 3 pi, and so it goes on forever. There's an infinite number of them, actually. What we're going to do, since we got more than just a single x up here, we're going to set this pi x here equal to 0. So we got pi x is equal to 0. We're going to take the pi x here and set it equal to pi here. And we'll take our pi x and set it equal to 2 pi here. Okay, now if I solve these, this one I'll divide both sides by pi. And we get x is equal to 0. This one I'll divide both sides by pi. And we get x is equal to 1. This one I'll divide both sides by pi. And you're going to start seeing a pattern here. We get x equals 2. Now, doing 2 of these isn't enough to see a pattern. But 3 is kind of showing us a pattern. 0, 1, 2, 3, and so forth. So our vertical asymptotes for this problem here occur at n, where n is an integer. Because it actually continue on the other side too, like -1, -2, and so on. So that's all our vertical asymptotes. And actually, I guess I could just say x equals n. Let me do that to make it a little bit cleaner. So x is equal to n, where n is an integer. Now this next one. It's got a trig one, but it's also got an x downstairs. So we've got f of x is equal to cotangent x over x. And same instructions, we want to find the vertical asymptote. Okay. First thing, we already said if we have a cosecant, secant, tangent, cotangent, we're going to rewrite them in terms of sine and cosine. So for this one, cotangent is cosine over sine. Now if you have a single fraction up on top, you can take that denominator, the sine x, and put it with this x. So this would be cosine x over x sine x. Well, let's set the denominator equal to 0. So we'll set x sine x equal to 0. zero factor property from college algebra says you got 0 on one side and you got two items factored on the other side written as a product, and you can set each factor equal to 0. So I'll set x equal to 0, and I'll set sine x equal to 0. Okay, so for our vertical asymptotes, well, the x equals 0 is pretty obvious. So that's one of them. X is equal to 0. Now for the sine x equal to 0. If I think where sine is equal to 0, we've already mentioned this. Sine is equal to 0 at 0, pi, 2 pi, 3 pi, so on. Well, this is 0 pi. This is 1 pi. This is 2 pi. And this is 3 pi, and so forth. And going the other direction the same way. Negative 1 pi, negative 2 pi. So it appears like there's 0, 1, 2, 3. Looks like there's integers before the pi again, isn't there? So I'm going to write this as x is equal to n pi, where n is an integer. Different ways you can write that. Personally, I like this form. But again, you're looking for the pattern when you're doing these trig problems. Save that. Now the next problems talk about the difference between a vertical asymptote and a removable discontinuity. So let me show this with an example. Okay, I got f of x is equal to x squared minus 1 over, let's see, x squared minus 4x plus 3. Now, if I factor the top and factor the bottom, this is the difference of two squares, and this would be the PSD method. Top part would be x plus 1, x minus 1. Bottom part would be x minus 1, x minus 3. Now, I notice that the x minus 1s cancel away. And I'm left with x plus 1 over x minus 3. Okay, I'm left with the x minus 3. So I set that equal to 0 and solve it. And this is a vertical asymptote. It's actually a discontinuity too. But specifically, they're asking the difference between a vertical asymptote and a removable discontinuity. So this is a vertical asymptote. Now up here, the x minus 1s I canceled, didn't I? I removed them from the problem. So if I set the x minus 1 equal to 0, this down here, and solve this, I get x equals 1. I canceled this, I removed it from the problem, so this is our removable discontinuity. I just can spell it. So that's the difference. If you can factor it and it cancels away, you remove it, that's a removable discontinuity. If it stays in the problem, and then that will give you a vertical asymptote. So let's take a look at these next two problems. Okay, so here we have f of x is equal to x squared minus 10x plus 16 over x minus 2. Well, bottom doesn't factor, but top will factor. It's the PSD method. It's x minus 2 times x minus 8 over x minus 2. Okay, so notice after I've factored top, factored the bottom, that the x minus 2 is going to cancel. I'm going to remove them. And I'm just left with x minus 8. So I don't even have a fraction anymore when I'm left. So there's no vertical asymptotes. But up here where I removed the x minus 2, if I set the x minus 2 equal to 0, this is going to give us x equals 2, so this is a removable discontinuity. Let's see number 9. F of x is equal to e to the 2 x minus 2 minus 1 over e to the x minus 2 minus 1. Now, in case you're wondering where they get these numbers from, notice here they're saying what's happening at x equals 2. Well, if I set the denominator equal to 0 and solve it, I get the x equals 2. So that's where they're getting that from. This one, they're asking about, again, x equals 2. Well, if you're wondering where they get that from, if I put 2 in here, 2 minus 2 is 0. E to the 0 is 1. 1 minus 1 gives us 0. So that's where they're figuring that from. Now, if they didn't tell us that, well, again, our issue would be where the bottom part here is equal to 0. And I'll do it down here. This one goes with number 9. If I set this, the denominator equal to 0, I'd get this. This is an exponential equation. You get the part of the variable and the exponent by itself. So I take the negative 1 to the right side, it becomes a positive 1. You take natural log of both sides. That's our next step in solving the exponential equation. And we got a property. It says natural log and e cancel each other away, so left with x minus 2. And natural log of 1 is 0. So then take negative 2 over, and I get a positive 2. So that's how on problem number 9, the directions came up with what's happening at x equals 2. It's got discontinuity there no matter what. Well, the top part can factor. This factors as e to the x minus 2 plus 1 times e to the x minus 2 minus 1. All over the bottom part. If you think of it backwards, it'll make sense, because these are conjugates. So remember, with conjugates, all you have to do is multiply your first parts together and your last parts. E to the x minus 2 times e to the x minus 2, you're going to add the exponents. Well, if you add them together, that gives you 2 times x minus 2. And then 1 times negative 1 gives you a negative 1. Now, after I've factored the top and factored the bottom, I see that e to the x minus 2 minus 1, e to the x minus 2 minus 1, they match. So those are going to cancel away. And I'm just left with e to the x minus 2 plus 1, which tells us that for this problem, x equals 2 is a removable discontinuity, because it canceled away. We removed it from the problem. Now the next problem is wanting you to find a limit. Find a limit as x approaches 2 from the left-hand side. That's what that negative means, of x squared over x squared plus 4. Well, let's first talk about the vertical asymptotes. I keep wanting to say vertical limit because there's a movie, Vertical Limit. Good movie. This is a fraction. For vertical asymptotes, if I set the denominator equal to 0 and solve it, I'm going to get x squared plus 4 equal to 0, and you get x squared equals negative 4. You're going to get an I. So there is no vertical asymptotes. Well, we don't necessarily care what's happening at 2, but this will allow us just to plug in a number on this particular problem. So if I put 2 in here, I get 2 squared over 2 squared plus 4. Gives us 4 over 4 plus 4, which gives us 4/8, which gives us 1/2 as our answer. Last one here. We've got the limit as x goes to 0 from the left-hand side of x to the third plus 3 over x. Now, this is coming from the left-hand side. We're looking as x approaches 0. Some of them you can eyeball and see. Like coming from left-hand side, I get closer and closer. Well, if I plug in x equals -1, I get 3 over -1. That's -3. If I plug in -1/2, well, you flip the fraction down here and multiply times the top, you get -6. It's obvious by if you keep plugging in like -100, I get -300. It's going to negative infinity. Now, a very easy way to do this is to look at the graph, though. So let's go do that. Press y equals, press clear. We got x to the third. So x caret 3 plus 3 over x. And then graph. And you can see coming from the left-hand side, first it goes up, but then it goes down forever. So as it gets closer and closer to x equals 0, it's going down forever, skimming it. Never touching it, never crossing it. That probably tells you what we have at x equals 0. It's a vertical asymptote there, but this is going to negative infinity. So let me save this. And that's our last problem, so let's stop the recorders.